So when it comes to more complicated circuits, we can't use the same analysis we used before because we just don't know what to do yet. So if I look at this first circuit here, it's more complicated. It has two resistors, as we say, in parallel. And it may seem obvious that if I say that the voltage across this resistor will be the same as this resistor, that may seem obvious, and in fact it's true, but what I don't know is that if I have a current here, how much goes here and how much goes here. Likewise, in the second figure, while it may seem obvious that I have one current that goes all the way around here, and therefore the same current through each of the two resistors, what I don't know is how much is in this one and how much is in this one. So we need some scheme to allow us to determine those things. The laws that allow us to determine how much current goes where and how much voltage is split are called Kirchhoff's laws, and there are two laws, the Kirchhoff current law and the Kirchhoff voltage law. The Kirchhoff current law says that if I have a node where wires come together, on each one of those nodes I can have a current coming in. So I1 coming in from the top, say I2 coming in from the right, I3 coming in from the left, but I can have more than three. What Kirchhoff's current law says is that the sum of those currents, all of them, has to equal 0. In practical terms, that means that if I have the sum of currents coming in equals the sum of currents going out. I can't have any buildup of current there, and so as I've drawn it, one of those currents, say I2, must be negative if both I1 and I3 are positive. But the Kirchhoff's current law is basically stated there at the end. That's the law stated mathematically. The sum of currents flowing into a node must be 0. Kirchhoff's voltage law, on the other hand, says that the sum of voltages around a loop must be 0. And so let me draw a circuit, a small circuit. So here I have a voltage source, here I have a resistor, and I come back, and I can have other things connected in various places, and so I can have nodes here. But that if I take a test particle and move it along, take it from the voltage source along this loop, and move it in that particular path, that its energy, when it comes back to the center, or to where I started, I start here, I go around the circuit, come back to where I started, that particle can't have changed energy. Therefore, the sum of voltages on each one of those segments is 0. So if I define a voltage change, V1 like this, V2 like this, V3 like this, and V4 like this, in each case I've drawn it, I'm going, as I go around clockwise, I'm always going from the negative to plus in each section, so as written, I'm gaining energy, but the law itself says that if I sum up over those voltage changes, I don't get any voltage change. Now, one has to be careful in the application of this law, but that's the statement of it, so that's the Kirchhoff voltage law. So now I can use those laws to solve these two circuits. Let me not use specific numbers as I got from my circuit, but I'm going to label each one of these. The current source is I, the 1K is R1, the 2K is R2, and now in this circuit I only have two nodes because all the three components, they all come together at those points, and So I'm going to use the Kirchhoff current law at each one of those sites to define my circuit, and I can also use the voltage law to tell me that the voltage here has to be the same as the voltage there, because if I go around in a circle like this, I have a plus change and a minus change of the same amount. I only have those two voltage changes, and they are the same. So let me write down all the things I need here. So I have a current I going like this. I have I1 here. I have I2 here. I have V2 here. And remember, current flows into the top side. And I have V1 here, current flowing in to the plus side again. So Kirchhoff's voltage law, oh, I also have a voltage here, which I may or may not know. Because it's a source, I don't have the convention, I just make it the same as the others. However, so using the Kirchhoff voltage law for V1 and V2, I have that V1 plus, well, let me go back. Let me define a path like I did before, going around like this. Now notice that as I go through R2, I go plus to minus. So I write down V2 because it's plus. But as I come around this loop going this way, I go minus plus on V1, which is the negative one. So Kirchhoff's voltage law in this particular case says that V2 minus V1 is 0, or V2 equals V1 equals V. Then if I use Kirchhoff's current law at this node, I just write it down. I1 here is flowing in, I1, so I without a subscript is flowing in, I1 is flowing out, I2 is also flowing out. So I can just write the Kirchhoff's current law as I equals I1 plus I2. And now I know that V1 and V2 are the same. I'm just calling them V. And so I can say I1 is V1 over R1 equals V over R1. I2 is V over R2. And now and I know that I equals I1 plus I2 equals capital I, which in this case is 10 milliamps. So I can then plug in for I1 and I2. That's voltage times 1 over R1 plus 1 over R2. And now, since I know what this is, I is 10 milliamps, I can solve for V, since I presumably know what R1 and R2 are. Notice I've here said that I can replace the two resistors in parallel with one resistor, and so I've come up with the well-known theorem for adding resistors in parallel. 1 over R equals 1 over R1 plus 1 over R2. So this famous equation is just the result of Kirchhoff's current law and Kirchhoff's voltage law. Let me make some room for myself to solve the second one. Here I'm going to jump the KCL step and just say that there's a current I that flows. So I equals I, and that flows through all the components. And Therefore, then I'll have also a V1 and a V2, each with the minus and pluses as appropriate. And so I can go straight to KVL and KCL, but the KCL gave me this. It just says that at this node here, the same current flows this way as that way, and at the node here and here, that's the same. So the current is everywhere else the same. Now, what KVL is going to tell me is that the total voltage here is just going to be the sum of V1 and V2. So KVL tells me V equals V1 plus V2. V1 is just I times R1. V2 is just I times R2. I can factor out the I then, and I know little I equals big I, R1 plus R2. And now I've solved this equation as well. I know what the total voltage is. It's the current, 10 milliamps, times the sum of the two resistors. And this is the famous combination of resistors in series. Resistors in series, you can have an equivalent R, which is just R1 plus R2. I needed equivalent there too. And so that's how we use Kirchhoff's laws to solve more complicated circuits.